Hello, this is Mr. Ferris. I'd like to walk you through the last little part of Lesson 4.2, which talks about the difference between the two different kinds of exponential functions that we can use to model real-life phenomena. So this is the last page, or the back half of the handout that you had in class. And I just want to make sure that I covered this a little more thoroughly. So basically, there's two ways that you can model exponential functions. The first model is the standard a times b to the t. A is considered the initial amount, b is considered the growth factor, t of course is the time variable or the input variable, and q is the output variable. And this is the type of equation we use anytime it's written as maybe we have a per year growth or per month or per minute, something like that. If it's clearly a per time unit growth, then we would use this function to model the growth. However, if it's a growth that is considered to be continuous, a lot of things in science, like perhaps bacteria growth, even some population growth, and certainly growth and decay of radioactive substances, generally will be continuous growth and decay, and so you will use a formula that has E in it. E, of course, is a number. It's a special number, kind of like pi, but it's a constant. It's a number. K is considered the continuous growth rate in its decimal form. T is still the input. A is still the initial amount, and Q is still the ending amount or the quantity that it grows to. So when you look at these two side by side, what I hope that you see is that there's not a whole lot of difference between them. They both have an ending amount Q. They both have a beginning amount A. They both have time as the input variable. Really, the only difference between these two models is where B is. In one version, we have e to the k in the other version. So honestly, a lot of times you may use either formula, and if you choose to do that, all you have to do is to make sure that the b is equal to e to the k. So both formulas many times are just as good to use on some sort of a real-life phenomena. You just want to look for keywords. Clearly, if you see the word continuous, why then you always default to the continuous formula. If it's per year, per minute, then you default to the a times b. But honestly, you can always go back and forth between these simply by converting b into e to the k. Or going backwards, if you had to find out what k was, of course, using our knowledge of logarithms, k then, since that's the exponent of e, k is the natural logarithm of b. Because we know any power of e is a natural logarithm. So k would be the natural logarithm of b. So armed with these two principles, that b in this formula is the same as e to the k in the other formula, or if you wanted to go the other way and figure out what k is, you could always just find the ln of b, and that would allow you to find k. So these are the two basic formulas that you want to use anytime you're kind of going back and forth from the continuous formula to the per time formula. So if you write those in there, those will be two helpful formulas when you're going back and forth. So now if we look at this table, just as an example of getting some practice at going back and forth between these two, here we have in the first column, we have the traditional a times b to the t version. The second column is the continuous version. And then on the other two columns, these are just the growth rates that we're going to write down. So just to review and to practice this new skill, if a was 5 and if b was 1.2, how could we convert this into the continuous version? Well, q is still q. The initial amount is still 5. But now where this number is, 1.2, well, that's our b. Where b is, we would like to replace it with e to the k. So we need to figure out what k is. We know how to do that because from this formula at the top, k can always be found by taking the natural logarithm of your b, the growth factor. So all you have to do is take out your calculator and calculate the natural logarithm of 1.2, and you'll find that it is 0.1823. So if we wanted to convert the per year formula into the continuous formula, we have now accomplished that. Those two formulas, both of them would be equally good at modeling the growth of whatever we're trying to model. So then if we answer the last two questions, the annual growth rate then refers to the first formula, because this was the per year formula. And you might remember from chapter 3 that the growth rate is sitting right here. It's the amount that's above 100%. So 0.2 is the amount above 100%. 0.2 we recognize as 20%. Hopefully that's familiar from a previous chapter we covered. A growth factor of 1.2 means you have a 20% growth rate. The continuous growth rate, however, the continuous growth rate is actually K. So if we go over here to the continuous formula and look for K, K is the coefficient of the T variable. And of course we would report it as a percent. So we would call it 18.23%. That would be the way we would write it. So in the equation, it will be in its decimal version, but when we're writing an answer like this, rates usually are written as percentages, so we'll write it as 18.23. Now I hope that in your mind, if you take a step back and you think about this, if you've got something that's growing at a particular rate per year, and it's 20% per year over 1 year, then the continuous rate ought to be just a little bit less, because if you consider that it's growing every single instant of every single minute of every day, of every week, of every month, throughout the whole year, well then it doesn't have to grow at as high of a rate if it's going to be compounded continuously. We covered that in chapter 3 as well. When you compound more often, you don't need as high of a percent to get the same outcome. So that should make sense. These two should always be very close together, although the continuous rate typically is a little bit less than the annual rate for the same phenomena that you're modeling. Okay, let's see if we can go backwards. Now, if we have the continuous formula and we know what K is, can we write the other version? The other version has to be Q equals, it will have the same initial amount, 59, but instead of e to the 0.09, we need to replace it with a growth factor, with b. So from our previous information up here, how do you find b? You find b by taking e to the k. So on your calculator, you type in e to the 0.09 power, and if you do that correctly, you should get 1.094. So the per year version of that same phenomena will be 59 times 1.094 to the t. So our growth factor turns out to be 1.094. So therefore, the annual growth rate, looking at our growth factor, is going to be 9.4%. It's the part that's above 1. So the annual growth rate, we would say, is 9.4%. The continuous rate was sitting right here by the t. That would be 9%. And once again, those two are very close, although the continuous is just a little bit less than the annual. That's typically going to be true. And then finally, if all you're given is the annual growth rate, and actually I guess it's a decay rate technically because it's negative, then the first thing we have to figure out is the b. And so if it's going down by 3.92%, to find the b, we will have to take 100%, and subtract 3.92%. That's how we find what b is equal to. So b will be equal to 100% minus this decay rate. So that's going to be 0.9608. So this will be Q equals. Now we don't have an initial amount given, so we'll just call that A. But we figured out because it's going down, remember, we now have to subtract that from 100% to get the growth factor. We learned that in chapter 3. So that'll be 0.9608. Or another way of thinking of it is if it's going down by 3.92% every year, that means there's 96.08% remaining every year. That's what the growth factor always tells us, is the percent remaining. And then we can go to the continuous version. To find the continuous, we need to find K. To find K, we have to take the ln of B. So if you take the ln of 0.9608, we're going to get a K number of negative 0.04. It's really like negative 0.03998 or something. So if you round even to 2 digits, it does round to 0.04. So that'll be the continuous version. And so the continuous growth rate is negative 0.04, but written as a percent, it would be negative 4%. Again, just a little bit less than the annual growth rate, more negative and less than. So there's the last little tidbit of information from section 4.2. Actually, that's not completely true. There's one more little tidbit. There's just this little notation that, you just got to watch out, because sometimes problems cannot be solved by logs. I know logs are wonderful and everything, and algebra. We've been using a lot of algebra. But there are just some problems that cannot be solved by logarithms in algebra, and here's why. If we know that population is growing exponentially, and we know that food supply is growing linearly, that's what some economists would predict, the year in which they first experienced food shortages would be the place where those two intersect. So if we were trying to figure out when is 2 times 1.02 to the t, when will that ever equal the food supply? That would be the time when we need to start getting worried about food shortages. When is that ever going to happen? When is this exponential function ever going to be equal to this linear function? So it would be like solving this. And so the traditional thing would be, you take the log of both sides. That allows to bring the t down in front. Well, the problem with that is, taking the log of the left side will bring t down in front. But taking the log of this side presents another problem, because now we got a log in here. So how do you get rid of the log? Well, you take 10 to the power, and you get in this vicious circle where you never really get t down in front, and it's never a factor, and it's never something that you can solve algebraically. It either becomes an exponent or becomes a log. So the only way to really do this is to do it graphically, because we know that exponential functions essentially are going to skyrocket eventually. Linear functions have a constant rate of change, but we know that somewhere out here, they're going to intersect. And that's what we're trying to find. When would this exponential function intersect the linear function? So we can solve this graphically. It's really not that bad if you use a good graphing tool like, for instance, Desmos. So here I've graphed the exponential, I've graphed the linear, and you can see they're starting to take off. And if you zoom out far enough, eventually you will find that, by golly, they do intersect out here somewhere, and it's right around 200 years. So in almost 200 years, they will intersect, and that's when perhaps we should find some food shortage issues. So some problems cannot be solved by logs or by algebra. You may have to graph them on your calculator and zoom correctly to find the time in which they would be intersecting. So there's the last little 2 bits of the lesson in section 4.2. Hopefully that would add a little bit of clarity. I know that was kind of fast, but you do have the option of pausing and rewinding. Of course, if you have any questions, as always, bring them with you to class next time. I'll see you then.